Okay, let's get started. This is the last lecture in this second mini-series of lectures. So hopefully it should be fun too. This is a topic that's orthogonal to everything else I've talked about, quality of service and interference in memory systems. And I can go on about this topic for a very long time. I'm sure just like Moin can go on about phase change memory for a very long time. But we'll stop at some point. Probably around 5 or so. Right? Okay. And let's see why this is not working. So we're here. This is lecture 3, main memory interference and quality of service. And I'll go through this very quickly. This is at the beginning of every lecture so that you can have. Remember, in the last lecture, we've covered a lot of emerging technologies, which Moin covered also. And we'll cover today memory quality of service. Last lecture, we've covered a little bit on flash scaling as well, area management and flash memory, if you remember. But today, we'll talk about main memory interference that affects all kinds of memory technologies. When you have multiple threads sharing main memory, there's a problem that happens. And I've shown you that problem earlier, actually. And I've asked some questions. How do you solve this problem? Today, we're going to look at some solutions to that problem. But I'll first discuss the problem again. We're putting more cores on a chip. You've seen the slide several times during these lecture series. This is not an up-to-date slide. People keep adding more cores. But basically, there's a good reason for this. What we ideally want is probably n times the system performs with n times the cores. But what do we get today? We've looked at this question from the point of view of scalability of parallel applications. We didn't get n times the system performance, right? Because of synchronization bottlenecks. And there were 3 fundamental bottlenecks in a parallel program or a parallel system. One was synchronization, load imbalance, and resource contention. And we've covered resource contention. Today, we'll talk about resource contention in a lot more detail, focusing on main memory. What do we get today? Well, it looks like my slide is acting up. That's PowerPoint always has bugs. But this I've shown you before. This is a study that we had done a long time ago in 2006. We ran 2 applications together on a 2-core system and measured the slowdown each experienced compared to when it was run alone. So MATLAB slows down by 7% only, whereas GCC slows down by almost 3x. So this is obviously unfair, right? You could argue that this is unfair. But even if you change the priority of the applications, you make this GCC high priority in the operating system, and nice MATLAB such that it's low priority, this doesn't change anything because the operating system still schedules these 2 applications on the 2 different cores, right? And they keep running. And we call this a memory performance hog at the time. And what happens is the reason for this memory performance hog, as I told you earlier, is the unfairness that happens in the DRAM controller. We did this experiment on a system that looked like this. You had caches that are not shared, or we ensured that the caches were not effective between the 2 cores, and DRAM controller was shared. When you're running MATLAB and GCC together, what happened was they both sent some requests to the memory system, and the memory system somehow prioritized MATLAB over GCC, right? The DRAM controller. And it kept prioritizing MATLAB over GCC. And you've seen the reasons for that, right? Because of the bank organization of DRAM. There were 2, the main reason was the scheduling policy over here. So we'll cover that again briefly and then go into solutions. Looks like my cores don't look as good, but this is another view of the memory system. Basically, memory system is a major shared resource, and this is why we see these unfair slowdowns. And it's not designed to be fair, as we've seen with caches earlier, as we've seen with interconnect earlier also. So these are the shared memory resources. You have shared caches, you have shared interconnect, you have shared memory controllers, you have shared buses, and shared DRAM banks. And we're going to focus today on the memory controller and the DRAM banks first, but then we're going to go back. The main problem is threads requests interfere in these resources, and they interfere unpredictably. And this is another view of the system. This is another slide that you've seen many times. The problem is a memory system does not distinguish between these different threads requests. Existing memory systems are free for all. They're shared based on demand. For example, we've seen the problem of one thread. If it wants the cache block, it gets it, right? There's nothing that says you should not get the cache block, and we looked at solutions for that. Control algorithms are thread unfair and thread unaware. Well, thread unaware, that's why they're thread unfair. Aggressive threads can deny service to others. because main memory systems do not try to reduce or control inter-thread interference. And that's why this happens. Actually, this happens, I'm going to abstract these two applications as streaming versus random access, because that's very similar to what their behavior is like. MATLAB is a very streaming application that's memory intensive, and GCC is a random access application that's not very memory intensive. And when you run these together, I'll call them stream and random, the memory system actually prioritizes the streaming application. And we'll take a look at the reasons for this. It's actually very easy to write these applications. I'll call the stream. This is part of the stream benchmark, a modified part of the stream benchmark that's used to measure memory bandwidth, main memory bandwidth in systems. And if you look at this, this is a memory performance log. This is basically very similar to MATLAB that I've shown you earlier. And you can easily write this today. Basically, this is a portion of it. We initialize large arrays A and B and copy array B into array A. And ensure that every access is a cache miss by basically changing the index such that your traversal goes through cache line boundaries. Right? That's stream. What are the characteristics? It has sequential memory access because the index is streaming. It has very high row buffer locality. Remember the row buffers we discussed in several lectures. It has 96% hit rate in the row buffer. And it's very memory intensive because we ensure that every access is a cache miss. Now to do the control experiment, we also constructed random access workload, which is essentially the same application, except when you're copying B to A, you don't do it sequentially, but you do it in a random manner. Right? If you look at the index, it's random here. As a result, this leads to random memory access, very low row buffer locality, because you're accessing arrays randomly. And it's similarly memory intensive, because we ensure, again, this randomness ensures that accesses are cache misses. Right? Of course, if you want to do this experiment on your own, you don't just copy this benchmark like this. If you do it that way, then the random function becomes a bottleneck, right? You're really measuring the time of the random function. You really want to equalize everything in these two systems, in these two workloads, to look at the effect of streaming versus randomness. So you need to pre-compute the index, and you need to access an index array to ensure that that random is not a bottleneck when you actually equalize the workloads. So if you run these two applications together, think about stream versus random or MATLAB versus GCC, although GCC is not exactly like random, but similar. What happens? This is the bank picture that I'm showing you earlier. A DRAM bank consists of two-dimensional array of cells. You have the rows and columns. And there's a row buffer, and data can only be read from the row buffer, if you remember. And this is the memory request buffer for this bank. And let's abstract everything such that there's only one bank. The blue thread T0 is stream. It keeps generating requests to the same row. And these requests hit in the row buffer. And as a result, the memory controller prioritized these requests. Because remember, the row buffer hit accesses were much faster than row buffer conflict accesses. Right? That's how the memory controller was designed. Because the access to the row buffer is much faster, the memory controller prioritizes the requests that hit in the row buffer. As a result, what happens is the memory controller keeps prioritizing T0's requests over and over and over until thread 0 stops generating requests to row 0. Right? Or maybe some memory controllers today actually have a hard limit saying that if I haven't serviced a request for maybe 10,000 cycles, that wasn't UltraSpark T1 Suns. If you remember the Niagara processor that we discussed, that had a limit of 10,000 cycles, I believe, saying that if I haven't serviced a request for 10,000 cycles, I will service it. So that would break the stream. But regardless, 10,000 cycles is a very long time. So with a row size of 8 kilobytes, a cache block size of 64 bytes, 128 requests of the streaming thread can be serviced before a single request of the random access thread is serviced. So this leads to unfairness, even if the memory intensities of both threads are the same, even if they're accessing memory at the same rate. Right? So the fundamental problem is that current controllers take advantage of the row buffer, and they use a scheduling policy that prioritizes row buffer hits over other requests, and that also prioritizes older requests over other requests. And both of these are unfair because this prioritizes streaming threads, and this prioritizes memory-intensive threads. Right? We don't want to do that. And in a system where you have a single thread, this could be a pretty good policy, right? Although we saw that even this is not a good policy because this is not looking ahead into what happens. So you can actually design a memory controller that operates using machine learning, reinforcement learning principles that gets you much better bandwidth. So it's a good heuristic. It's not the best heuristic. It's simple. But in a single core system, it makes sense, perhaps. But in a multi-core system, when multiple threads share the DRAM system, then it breaks down. And we've actually looked at, so when you run stream and random together, what's the effect of this on a real system? Again, these are results on a real system, Intel Pentium D running Windows in 2006. And if you look at the results, stream slows down by 18%, random slows down by almost 3x. And this is consistent with other applications, real applications as well. You can run stream with GCC, you get something similar. You run stream with Microsoft Virtual Machine at that time, and you get something, again, similar. So you basically keep denying service to the application that's running together with you if you have a memory hog. So we called this the memory hog at the time. And this becomes greater as you keep adding more cores. These are actually simulation results with 4 core. These are 4 different applications. And these are the slowdowns they experience when they're running together compared to when they're run alone. libQuantum is very similar to the stream workload. It's a quantum computing simulator. And it's a very streaming workload. It gets a lot of cache misses. So it slows down by only 5%. Whereas Omnet, which is not very memory intensive, slows down by almost 8x, 8 times. And H.264F, which is a video encoder decoder, slows down by almost 5x. So this may be a critical application, right? You may actually be watching video while doing some quantum computing simulation in the background. Like people used to do these search for extraterrestrial intelligence workloads, right? They used to run those on their computers for a long time. So you could be doing that, right, to search science in the world. But if this is denying service to your video, maybe that's not a good idea, right? You're losing throughput. I mean, that's a cooked up example, but there are real scenarios where a cloud computing scenario, for example, somebody might be doing time critical work. Somebody else might be doing a batch job, batch simulation, just like this. Batch simulations are usually very streaming sometimes. And as a result, this program may be denying service to this time critical job for someone else. So what are the problems with this? First, you have a vulnerability to denial of service. Basically, you have this memory performance hog. It's basically, and it's very easy to write it, again. It's really easy to write this program. You could do it today. In fact, today's systems have incorporated a little bit of quality of service in multi-core, in general purpose multi-core systems. But still, you can overcome that. The second is, you cannot enforce priorities or service level agreements. If you really want to take and prioritize this H.264F, there's no way of saying this is high priority because those priorities will not get communicated to the memory controller today. The only way you could do this is basically descheduling some applications. So you could run H.264F by itself, but then you would be losing a lot of throughput. Why are you building a multi-core system, right? Then the third problem with this is you get low system performance. Even though this core may be making progress, these other cores are making very slow progress. And in fact, this core is making very slow progress to begin with because it's very memory intensive, right? So we're actually doing the opposite thing, even if we want high system performance. We want to prioritize the threads that are memory non-intensive if you would like to get high system performance. So basically, what we have with unfair sharing of the memory system is an uncontrollable, unpredictable system. We cannot control it, and we cannot predict what kind of performance we would get out of it. And that's not desirable. And this actually happens with many different workloads. These are just examples. You can, for example, in some mix of applications, one application may get 8x slowdown. In other mix, it may get 4x slowdown. So it's very unpredictable, right? Your performance depends very much on your core runners. And you also have all of these other problems. And this becomes actually even worse as you scale the system. This is just one example. We've talked about on-chip interconnects. You can connect the cores via packet-switched routers on chip. You get something like this. You can actually do denial of service on this also, right? And this may be unintentional. So this may be totally unintentional. You can have 8 cores like this. I call them the attackers. And some other application over here. It's stock option pricing, just for fun. This is actually a real result, by the way. Black-Scholes is a stock option pricing application from Parsec Workload Suite. It does the stock option pricing with some learning methods. And you can, for example, all of these may be accessing a memory controller over here, right? And as a result, while this application is trying to communicate within its cores, this is basically flooding the entire system. And you can get slowdowns that are ridiculous, in fact, like 5,000x. I mean, nobody would build a system like this, but if you build it the way on-chip networks are designed today, you could get something like this without quality of service. So we'd like to, basically, how do we solve this problem? We don't want any of those issues. We want to build a controllable system. The problem is inter-thread interference is uncontrolled in all memory resources: memory controller, interconnect, and caches. We've looked at solving the problem for caches a little bit. In fact, I've told you about utility-based cache partitioning, which Moin came up with. He didn't talk about it today, but that actually spurred a lot of work in the area. Basically, we need to control it. In other words, we need to design an interference-aware or quality-of-service-aware memory system. And I think there are three key questions, three key challenges to solve to enable this. First, how do we reduce inter-thread interference? And what do I mean by that? Basically, threads are interfering in the memory system with each other. And if we reduce that a little bit, we can get much better system performance and much better core utilization. So instead of prioritizing the cores that are making slow progress, maybe we want to prioritize cores that are making fast progress. That way we reduce the interference rate. We can also reduce request serialization that way and core starvation. I'll show you techniques that reduce inter-thread interference. Second is, how do we control this inter-thread interference? You can think of this as inter-core interference also. But this happens in any kind of multi-threaded system that are, where threads share the memory system. How do we provide mechanisms to enable the system software to enforce quality of service policies? Maybe we want system software saying, I don't want this application to be slowed down by more than this much. Right? All the while providing high system performance. This is key, right? Because it's really easy to control inter-thread interference if you don't care about performance. You design a 1,000-core system and you run only one core. And you provided all kinds of fairness and predictability, but that's not interesting, right? And third is, how do we make the memory system configurable and flexible? The key idea here is, sometimes we would like fairness, sometimes we would like throughput, and sometimes we would like a mix of the goals. Some applications do not care. Some applications we really want quality of service guarantees. And memory systems should be able to satisfy all of those at the same time and at different times also. So we would like to enable flexible mechanisms that can achieve many goals at the same time. Provide fairness or throughput when needed, and satisfy performance guarantees when needed. So there are two major approaches that we've been looking at, and I think there are two fundamental approaches to this problem. One is smart resources, I call it. Basically, you can design each shared resource, memory controllers, interconnect, and caches, to be intelligent, to have this interference control and reduction mechanisms that can be made configurable. And that's one solution. Basically, you change the memory controllers such that they're fair now and they're configurable now, right? You change the interconnect such that they're fair and configurable. You change the caches such that they're fair and configurable. And I'm going to cover a lot of solutions on the memory controller space here. We've discussed caches a little bit. We didn't discuss interconnect quality of service that much, but you had the slides in the rest of the interconnect lecture. So you can look at that. The other opposite end of the spectrum is keeping the resources dumb, right? You can say, OK, I'm designing the memory controller to be unfair, such that it optimizes to be row hit first and oldest first, right? Or a self-optimizing memory controller that does machine learning. But you can design mechanisms into the system such that they monitor what's going on between different threads, which threads are interfering with each other, which threads are being slowed down, which threads are being sped up unnecessarily. And you can control this interference in the periphery, by controlling injection or by mapping data differently or by mapping threads, scheduling threads differently to the system. And I'll cover this also. There are several solution directions. You can throttle the sources, for example. If you figure out that one application is interfering too much with another application, you can say there could be control in the system saying that this application is interfering too much, so throttle it. Don't inject more from this application, right? We call this source throttling. And we've actually covered source throttling a little bit in the context of interconnects, right? Remember, we did heterogeneous adaptive throttling at the periphery. It's the same idea, but we're going to use it for the entire memory system this time. You could do better data mapping to memory controllers such that interference is reduced. And you could do better thread scheduling to cores such that interference is reduced. And we've seen actually examples of this in caches. We talked about page coloring, right? You could map the data using page coloring such that different threads use different indices of the cache, and as a result, they do not interfere with each other. Teşekkür ederim. So we'll try to cover a lot of these approaches. I don't think I'll be able to finish everything here. But we'll start with quality of service aware memory controllers first. Any questions so far? No? Everybody is interested in Chai now? OK. Well, feel free to ask questions. You know that very well. But we'll basically cover these two fundamental approaches. And by the way, these fundamental approaches are combinable also. You can combine them and get a much better system. And I'll show you that you can get a much better system by combining data mapping to memory controllers as well as adding a little bit of quality of service aware memory scheduling. So doing both. Doing both is usually better in this case, as long as you can combine them in a smart way. But let's focus on the memory scheduling first. And I'll spend quite a bit of time because we've been looking at this for a long time, actually, starting with late 2006. After the memory performance attacks paper, we've started developing different solutions and discovering different problems in memory controllers at the time. And I believe a lot of the ideas that we discussed over here will be applicable to other controllers as we add more technologies into the system. So if you look at the memory controller sits between the cores and memory. And its job is to resolve memory contention by scheduling requests. The key question that we're going to try to answer is, how do you schedule requests to provide high system performance, high fairness to applications, and some configurability to system software such that the system software can control which application gets how much bandwidth, how much performance. Obviously, to be able to do this, memory controller needs to be aware of threads. I do not know of any way of doing this without being aware of threads. And if you figure it out, I'd be really interested in learning that. But that's tough, I think. So let me give you an evolution of this. Basically, this is a very quick summary of what is to come in the next 2 hours, I believe, or maybe 3 hours. Basically, when we first started, our key idea was we saw these slowdown curves, right? And our key idea was, if these slowdown curves are so unfair, why don't we just balance them, right? Instead of one application slowing by 5% and another application slows by 8x, why don't we make everything 4x? So that was the idea here. Stall time fair memory scheduling. Somehow estimate, you design the memory controller to estimate and balance the thread slowdowns. And the key takeaway we found, I'll go into a little bit more detail over here soon. The key takeaway we found is, if you do this, now threads progress proportionally, right? Their slowdowns are equal almost. That improves performance, especially when threads are memory intensive. But this is not the best for performance. So we'll see that this is not the best system for performance. Later, we've looked at parallelism-aware batch scheduling. And here there were two key ideas. One is ranking the threads and servicing the threads in rank order such that we can preserve bank parallelism, and batching the request to prevent starvation. I'll just give you the idea of within thread bank parallelism so you can keep this in mind. So if you look at these two banks, and if you have two threads accessing these two banks, what the memory controller might do is service requests like this. You have thread B's request, red request over here, and this is where we need the red again. It works. In bank 1, thread B's request is prioritized, where thread A's request is not prioritized. On bank 0, thread A's request is prioritized, where thread B's request is not prioritized. As a result, you lose parallelism in the threads, right? Each thread's requests are serialized across the banks. You get a service timeline that looks like this in two banks. The blue one first, red one next, and the red one first and blue one next. This is bank 0, bank 1. As a result, both threads wait for 2 memory access latencies, right? If these are the only requests they are waiting for. But you could do a much better thing by ranking these two different threads. What happens in this case is, let's say we said the memory controller ranks thread A higher than thread B and preserves that ranking across all the banks. If you do that, you get this, basically. You get this reordering. And you get the blue thread prioritized on both banks at the same time and red thread prioritized on both banks at the same time. And what happens as a result is a memory service timeline that looks like this, much more regular. There's no serialization of requests within a thread across different banks. And as a result, you get much reduced weight on thread A. And you save cycles. as you increase the number of banks and the number of cores that are accessing memory, this becomes more significant. So that's the key idea of exploiting within-thread bank parallelism. Basically, you make the memory system more regular such that you don't lose bank parallelism. And I'll discuss how we do that when we get to parallelism over batch scheduling in more detail. Well, I guess I'm discussing it right now, so it'll be easier later on. Basically, there are two key principles to do that. You schedule requests from a thread back-to-back to a bank. This preserves each thread's bank parallelism. But this can actually cause starvation, as we will see later in a little bit more detail, because when you schedule request threads, threads request back-to-back to the same bank, it might be that that thread generates more requests, right? And if you keep doing that, you will be servicing only that thread for a long time. So the second principle is to group a fixed number of oldest requests from each thread into a batch. So basically, memory controller looks at its queue and groups a bunch of requests into a batch, saying that I'm going to service these requests first, and I'm not going to consider anything that comes afterwards. This idea has been used in disks for a long time, for almost 50 years now. Basically, if you have many requests coming into the disk controller, you batch some requests saying that I'm going to service these first, such that no one else is serviced. And after that, I'm going to go back to the next batch. So I'm going to discuss in a little bit more detail. But basically, if you do this, this eliminates starvation and provides fairness and provides a substrate for doing parallelism over scheduling. Let's take a look at how this looks like. You have bank 0 and bank 1. And let's say you have requests from 4 different threads, 0 through 3. Memory controller looks at this request queue and batches some requests. And I'll tell you how this happens in a little bit more detail later on. And within the batch, the memory controller takes each thread's requests back to back. It takes requests from thread 1, services them. And requests from thread 3 arrive, but they're not included in the batch. Right? And then the memory controller takes requests from thread 0 and services them back to back. So their parallelism is preserved. And then the memory controller takes requests from thread 3, services them back to back. And note that it doesn't service thread 3's other requests that are outside the batch. So this prevents starvation. And this provides fairness to the system. And then the memory controller takes thread 2's requests in the batch and services them back to back. And once that batch is done, the memory controller moves on, forms a new batch. So it's again a very regular system. You preserve bank level parallelism, and you also provide fairness and non-starvation guarantees, because you always finish a batch before moving to the next batch. And we'll discuss in a little bit more detail.
Your window size is important.
That's right, exactly. And we will get to that. That's perhaps the most important choice in designing a scheduler like this. And people have looked at it. People have looked at batching from the point of view of disks, because in disks you really want to prioritize those requests where your head is going to move to next, right? Disks are sequential access is much more important much faster than random access. If your head is getting closer to what you're going to access, you would like to service that. But there's a trade-off again, right? You could actually deny service if you keep injecting requests that is going to the locations where head you're going to move next, right? So that's why people have employed batching in disks, such that this kind of unfairness, starvation does not happen. We're essentially exploiting the same idea, and we have a similar trade-off in the sense that how big is your batch, because that also determines your throughput as well as fairness. And we'll discuss this in a little bit more detail. It's actually a lot of fun to think about it. OK, so that was the idea over here in the second attempt at our solution. The takeaway: preserving within-thread bank parallelism improves performance, and request batching improves fairness. And we will see that this is a better performing and much more fair system than the first solution we've discussed. Whether I'm going to discuss all of these in a little bit more detail. I'm just giving an outline to you. The third solution is the Atlas memory scheduler. Basically, I'll get to this in more detail, but the idea here is if you look at this, these are not prioritizing those threads that are not very intensive. If a thread is generating requests only once in a while, it means that if you service that request, it'll go back to its computation phase, and it'll run fast, right? Whereas if you don't service that request, it'll wait for a long time just for one request. So it actually makes sense to prioritize those threads that are not very intensive, because that improves overall system performance, because those threads have the most potential to keep their cores busy. Whereas threads that are generating lots of requests are slow anyway, right? If you delay them a little bit, maybe it doesn't matter that much, right? Whereas if you delay a thread that has only one request a little bit, that matters for that thread. And the idea in Atlas Memory Scheduler is based on this idea. Basically, prioritize the thread that have attained the least service from the memory scheduler. And the takeaway we found is that prioritizing these light threads improves performance. And you'll see that later on. This improves performance much more compared to these other ones. But it's not as fair. So we're going to try to fix that problem later. The next solution was the thread cluster memory scheduling. And here we wanted to get the best of both worlds. We wanted to get high system throughput as well as high fairness at the same time. And it turns out doing this with a single policy is very difficult. So we designed a heterogeneous scheduling policy. Basically, the idea is to cluster threads into multiple groups, latency versus bandwidth sensitive, and prioritize the latency sensitive ones, and employ a fairness policy in the bandwidth sensitive group. Basically, in the bandwidth sensitive group, you provide fairness. And you shuffle through the threads such that each one gets the highest priority at any given point in time. And the takeaway here is, I've actually discussed this very briefly when I talk about asymmetry, right, in the first mini lecture series. Maybe you don't remember because I talked about a lot of things. But basically, the takeaway is the heterogeneous scheduling policy that is different based on thread behavior maximizes both performance and fairness. So you can actually achieve the best of both worlds. Again, with heterogeneity, right? That was our motivation for heterogeneity, and this is one example, and we will see. So later, we looked at the dumb resources approach a little bit. The idea here is you can actually partition the channels across different threads to reduce their interference. Basically, and if you do that, and also prioritize latency-sensitive threads in the scheduler, you can get a much more higher performance scheduler. So we'll discuss in a little bit more detail. Basically, the key takeaway here is if you intelligently combine application-aware channel partitioning such that you reduce interference, application A goes to this channel, application B goes to this channel, and also do slightly intelligent scheduling, that provides better performance than doing either alone. So we'll see that this is a better performing scheduler than thread cluster memory scheduling, although it's not as fair. Okay, then we looked at the idea of how do you do memory scheduling for parallel applications. So far, I've discussed multi-programmed applications. And some of these are actually applicable to parallel applications, and they do improve performance in parallel applications as well. But if you're more aware of the synchronization in the parallel applications, you can do much better. I've actually discussed this idea a little bit. Basically, if you identify and prioritize limiter threads or bottleneck threads, critical threads, in a multi-threaded application, and convey this to the memory scheduler, the memory scheduler can prioritize those threads, and all other threads that are not critical, the memory scheduler can try to ensure that they do not become critical. That's the idea. Somehow identify those requests, and you could identify those requests similar with mechanisms that are similar to bottleneck identification and scheduling that we've discussed earlier, and convey this information to the memory scheduler so that those threads get prioritized. All other threads, memory scheduler shuffles through them such that they make fair progress. And if you do that, if you do this prioritization carefully, you improve performance in a parallel application significantly. And if we have time, I'll discuss this in a little bit more detail. Later, we looked at how to actually design the memory scheduler for a heterogeneous system. And we'll see that the problem becomes a little bit harder if you integrate a GPU and a bunch of CPUs on a system, because GPU becomes very intensive in terms of memory. And we'll see that you can design, and the problem here is because GPU floods the memory system, it generates thousands of requests. You need a request buffer that's very large. And how do you, then how do you design the memory scheduler that operates on a very large request buffer? If you have a monolithic scheduler that examines the huge request buffer, it becomes unscalable. So we've divided the memory scheduler into multiple distinct stages, where each stage is significantly simpler than a monolithic scheduler, and each stage performs a different task. We'll see that you do row buffer locality in one stage, you do application-aware scheduling in one other stage, and you do DRAM command scheduling in the third stage, and you divide the buffers such that you don't have a monolithic buffer that does everything. That way you can get a much simpler scheduler that is application-aware, and that works on very large request buffers if you combine them, and that gets much better performance and fairness compared to previous schedulers, at least for a heterogeneous system. Okay. I guess it's a very long thing, but you don't need to get all of it. This is the latest work that I will also talk about. Basically, we have been moving toward the direction of how do we get predictable performance. So can we actually guarantee the slowdown of a thread? And in this latest work by my student Lavanya, the idea was to somehow estimate the performance of a thread when it's running together with other threads accurately. Remember, we were actually estimating the slowdown with one of the previous works, stall time fair memory scheduling, but we were not very accurate. So Lavanya developed a mechanism that actually estimates the slowdown very accurately. And the key idea over here is you can take the request service rate of a thread as a good proxy for its performance. And you can get that request service rate alone by prioritizing that thread in the memory scheduling for a while. And if you do not understand this yet, we'll get to it. But once you get that slowdown, now you can enable a bunch of different scheduling policies. You can expose the slowdown to the memory, to the operating system also. And you can do different kinds of scheduling to provide predictable performance. So we'll get to that. These are some things I will not talk about, but we've looked at how to incorporate prefetches into the memory scheduler. And I think this is a very important system design. This is Iman's work, Iman Ibrahimi. Basically, the idea is to prioritize prefetches based on how they affect system performance. If the prefetches are accurate, you can treat them as demands. If the prefetches are inaccurate, you can treat them as lower priority. Then the key question is how do you distinguish between an accurate and inaccurate prefetch, right? In fact, even accurate prefetches can degrade the performance of a system if they're interfering with demand requests of other applications. So we've developed some mechanisms that actually try to solve this problem. And the takeaway is, again, carefully controlling and prioritizing prefetch requests improves performance and fairness. And this is summarized in a lot of different works. I'd be happy to talk about them some other time. And the last thing is, which is a very interesting direction, I think, is can you coordinate the design of caches and the memory controller together such that they're aware of each other? We've been looking at DRAM-aware last-level cache policies. And the idea here is to design the cache eviction and replacement policies such that they proactively exploit what's happening at the memory controller. So if a row buffer is open, for example, at the memory controller, and maybe the cache is aware of that, and the cache streams out the blocks that you need to evict that will go into that row buffer, right? That way you improve row buffer locality while evicting cache blocks. So by coordinating the design of DRAM and the last level cache, you can get much better performance and fairness again. Because you're designing the system in a more integrated manner, right? Right now, when you evict a cache block, it goes to a row that's not open. You get row conflicts. But if you do this proactively, say if you do it in a manner such that the memory controller requests requests cache blocks that go to this row that's open at this point, you can get much better performance. Okay, any questions? I've given you a fire hose of different techniques, some of which I will cover. Actually, many of which I'll cover. But if everybody is okay with it, we can start with the first one. I guess I'll first take a sip from my chai. I'm sorry? It's warm, but it's not as hot as before. It'll get cold soon. Okay, so I'll briefly cover stall time fair memory scheduling in a little bit more detail. I will not go into too much implementation details, but I'll tell you some of the trade-offs. So remember, this was a picture with a 4-core system, right? Some applications slow down very little, some applications slow down a lot. And there were a lot of problems with it. Denial of service vulnerability, unable to enforce priorities or SLAs, and low system performance. So we wanted to solve this problem. And the first idea that comes to your mind, perhaps, at least to our minds, is if this is so unfair, why not make them fair here, right? That's the idea. So we're going to try to achieve that. The goal is to have threads sharing main memory experience similar slowdowns compared to when they're run alone on the same system. And that was our definition of fairness. By the way, this is not the only definition of fairness, and we're going to go to a better definition of fairness later on that I believe is better. But this is all debatable, right? Fairness is a very tough thing to debate, even in the political spectrum. Actually, perhaps much harder in the political spectrum than here. But basically, that was our idea. And if you actually do this, the hope is that it also improves overall system performance by ensuring cores make proportional progress. Right. Now your cores are having proportional slowdowns. And the idea to achieve this is to have the memory controller estimate each thread's slowdown due to interference and schedule requests in a manner that balances the slowdowns. And this is the paper that describes the idea. So how do you do this? That's the key question. It turns out it's not going to be as easy. So a DRAM system, we've designed a DRAM system to be fair if it equalizes the slowdown of equal priority threads. Equal priority is very important, relative to when each thread is run alone on the same system. So I'm going to define DRAM-related stall time as the time a thread spends waiting for DRAM memory. And you have two versions of this. One is stall time shared. This is the DRAM-related stall time when the thread runs with other threads. And the second one is stall time alone. This is the DRAM-related stall time when the thread runs alone on the same system. You don't have any other threads on any core. So memory slowdown is defined as stall time shared divided by stall time alone. So it's the relative increase in stall time. So if a thread is stalling for 1 second when it's running alone versus 10 seconds when it's running together with other threads, its memory slowdown is 10. Right? So a stall time fair memory scheduler aims to equalize this value, memory slowdown, for interfering threads without sacrificing performance. Well, that's the hope. That's the goal, again. So the nice thing about this metric is it considers inherent DRAM performance of each thread. You could say, why not equalize stall time shared? Consider the alone performance of each thread. That would be very unfair in some ways. And this also aims to allow proportional progress of threads. And proportional progress is actually good for the operating system, because the operating system, when it schedules threads to cores, it assumes that these threads will hopefully make some progress, right? And the hope is that it's proportional. But today we get, of course, some threads not making any progress at all for a while. So how do you actually, what is the algorithm once you can estimate memory slowdown? So for each thread, the DRAM controller tracks stall time shared. And this is actually easy to do because the applications are running together with each other. Right? It also estimates stall time alone. This is the harder part. And how do we do that? I'll discuss this in a little bit more detail later on. But basically, the memory controller keeps track of the interference that happens between these different threads and subtracts those interference cycles that a thread experiences from stall time shared. So let's say you have threads A and B, and memory controller preferred B's request over A's request when A had a request. Now A incurred some interference, right? The memory controller knows how long A was delayed. So we'll call this interference cycles. And this is an excess cycle. This is an extra cycle that wouldn't have happened, right? So the memory controller keeps track of these extra cycles for each thread, and it subtracts those extra cycles from stall time shared to get the stall time alone for each thread. Now, it's not as easy as I described because there are many sources of interference that happens in a DRAM system, like row buffer, for example. A thread opens a row buffer, it closes the row buffer that another thread needs. How do you figure out how much delay happened because of that? Well, you can figure it out actually if you have shadow row buffers. You need some hardware cost, right? Basically, you can emulate the DRAM system as if the thread was running alone, but that comes at a high cost. So let's assume that you have these two values somehow. And this is the hard part. This is the reason this memory scheduler is hard to implement, because this estimation is difficult. Each cycle, the memory controller computes a slowdown value, stall time shared divided by stall time alone, for threads that have legal requests, that can be scheduled at that point. Some threads may not be able to schedule requests because there may be a bank conflict, right? It also computes unfairness using these values. This unfairness, remember, it's defined as the maximum slowdown in the system divided by minimum slowdown in the system. The thread that has the minimum slowdown and the thread that has the maximum slowdown, you take them and divide their slowdowns, and that's unfairness. And I'll give you an example. If unfairness is less than a value alpha, this is specified by the system software. Basically, if unfairness is tolerable to the system, we use DRAM throughput-oriented scheduling policy. Basically, we use row hit first scheduling that we've discussed before. Or some other scheduling, machine learning-based scheduling, right? Otherwise, if unfairness is greater than or equal to alpha, which means that unfairness is not tolerable to the system, you should be fair, we switch to a fairness-oriented scheduling policy. Basically, the requests from the thread that has been slowed down the most are prioritized in this case. And all else being equal, row hit requests are prioritized over others, and oldest requests are prioritized over others. Basically, that's the idea. You switch between throughput-oriented and fairness-oriented scheduling policies depending on the value of the unfairness.
I have a problem with each cycle. Actually,
Yeah.
you should not do that at each cycle, that computation, because it will just give you a big overhead. There must be a greater window for this computation.
Yeah. So we've actually looked at other windows. This is just a outdated slide, I would say. You could do it each cycle. You could do it over a window also.
Yes.
And there's a trade-off as to how fast you can react, obviously. But yes, with each cycle, it becomes a little bit harder to design.
Yes.
Yeah. That's a very good point. Hopefully, we're going to fix all of these problems with the most recent work that actually doesn't do everything in each cycle, but has longer intervals. Okay, so how does this scheduling policy, assuming that this is implemented somehow, how does the scheduling policy prevent unfairness? This is the same picture. We have thread 0 and thread 1 here again. Remember, thread 0 is the blue thread, thread 1 is the red thread. And this is the unfairness value the memory controller keeps track of. Initially, these are 1. And unfairness is 1. And maximum tolerable unfairness is 1.05. That's the alpha value. Let's say thread 0 accesses the first request. Thread 1 needs to access row 16. But its request is not prioritized because thread 0 is accessing the row that's in the row buffer. As a result, thread 1 gets delayed, right? The memory controller keeps track of this delay. So thread 1 slowdown becomes 1.03. And the unfairnesses in the system is, remember, maximum slowdown divided by minimum slowdown, 1.03. And the memory controller checks for the next request whether unfairness is less than alpha. It is less than alpha. So it keeps going with the throughput-oriented scheduling policy. So it prioritizes thread 0's request over thread 1's request, right? Because this sits in the row buffer. That's throughput-oriented scheduling policy. And this causes slowdown to thread 1. And its slowdown increases, and unfairness increases. And unfairness becomes unbearable at this point because 1.06 is greater than 1.05, right? As a result, the memory controller switches to the fairness-oriented scheduling policy. It prioritizes the requests from thread 1, which is the maximum slowdown thread, instead of picking the requests from thread 0, which goes to the row buffer again. Right? And this changes the row buffer, and thread 1 gets serviced. As a result, thread 0 gets slowed down now, right? And this increases thread 0 slowdown and reduces unfairness in the system because 1.06 divided by 1.03 is 1.03 now. And this is still less than, now it becomes less than alpha. So the memory controller switches to the throughput-oriented scheduling policy, which is oldest first. So it takes thread 0's row 0 in this case. There are no row buffer hits in this case. And doing this causes slowdown to both threads in this case because thread 0's row buffer was changed, right? If it were running alone, its row buffer would have been row 0. As a result, it got some slowdown also because some other thread interfered with it. But slowdown is still, unfairness is still unbearable, is still below the alpha value. As a result, memory controller keeps going with the throughput-oriented scheduling policy. And this increases unfairness again, and so on and so forth. As a result, memory controller keeps switching between the fairness and throughput-oriented scheduling policies. Right? So it's pretty simple, conceptually. Implementation-wise, it's a little bit harder. So the upsides, that'll be the downside part. Upsides, this is actually first work on fair multi-core memory scheduling that tries to solve the problem. It's good at providing fairness. The solution is, I think, conceptually nice, and we're going to try to get back to it, actually, with the latest work. And being fair actually improves performance. I didn't show you results with this. I'll show you results later on in the next work. And being fair improves performance because you get proportional progress. Some cores do not wait, right? You get much better core utilization. Downsides, it doesn't handle all types of interference, as I will show you. It's somewhat complex to implement. It's actually complex to implement if you want to do exact slowdown estimation. Basically, you need to model everything in a memory controller for every thread. And that's very tough. We didn't do that, of course. We approximated. But once you approximate, your slowdown estimations can be incorrect. Right? So in fact, I will show you results later on that the slowdown estimations are incorrect by 30% across a large variety of workloads. But that's OK if you want to provide fairness, because what we're trying to do is really, as long as you get this thread that has been slowed down the most, you achieve the goal. We're not trying to provide predictable performance. You really need accurate slowdown estimations if you want to say, my slowdown should not be more than this. OK. Any more questions on this? OK, I'll keep going then. So next, we realize there are other types of interference also. And one other problem due to interference is that memory level parallelism of a thread is destroyed. And we've talked about memory level parallelism before, right? We talked about MLP over cache replacement, which Moin knows a lot about. Basically, processors try to tolerate the latency of DRAM requests by generating multiple outstanding requests. The idea is memory level parallelism. And there are many ideas that exploit this: out-of-order execution, non-blocking caches, run-ahead execution. This is effective only if the DRAM actually services these multiple requests in parallel in the DRAM banks. Right? When multiple threads share the DRAM controller, and if the DRAM controllers are not aware of a thread's memory level parallelism, this may not be the case. DRAM controllers can service each thread's outstanding request serially and not in parallel. I showed you this earlier, and I'm going to go into detail a little bit more. Let's take a look at a pictorial example. You have a single thread, thread A, running on one core. Assume that there's only one core now. And you have memory with two banks. This thread generates two DRAM requests. And these requests are sent to the memory controller. Memory controller first schedules the first one. And then the memory controller schedules the second request. And both threads are request in parallel. You see that the memory, in this timeline, both bank 0 and bank 1 are servicing requests from the same thread. And when both requests are done, the thread can continue computation. If you look at this, the bank access latencies of the two requests are overlapped. And each thread stalls for approximately 1 bank access latency, right, instead of 2. That's the beauty of memory level parallelism and bank level parallelism. Let's take a look at what happens if you have two threads that do exactly the same thing I showed you earlier. Thread A and thread B both compute. They generate two DRAM requests. And these requests arrive at the memory controller this way, let's say. And the memory controller first takes thread A's request to bank 0, schedules it. Then it takes thread B's request to bank 1, schedules it. And while these requests are being serviced, both threads stall. Then the memory controller takes thread B's request to bank 0, because thread A's request to bank 0 is done, and schedules it. Then it takes thread A's request to bank 1 and schedules it. And while both of these requests are going on, both threads stall again, right? Because they don't have all their requests come back to the cores yet. And once both requests come back, the threads can continue computation, right? Now, if you look at this, bank access latencies of each thread are actually serialized in this case. And each thread stalls for approximately 2 bank access latencies. This is with the baseline scheduler. So the key question is, can we do much better than this? What would a parallelism aware scheduler do? And I've already shown you what it would do, but I'll give you it in a different way. Basically, these two threads compute and they generate 2 DRAM requests each. These requests arrive in the same order that I've shown you before. Instead of, well, the memory controller, let's say, takes thread A's request to bank 0 and schedules it. And while this is going on, instead of taking the next request, which is thread B's request to bank 1, which would destroy the parallelism of thread A in the memory system, in the banks, the memory controller realizes that there is another request from thread A to bank 1, and it takes that request and schedules it. So instead of doing scheduling in the order, in the request order, the memory controller actually takes requests from the thread order, right, back to back from the same thread. As a result, these two requests get serviced in parallel and both threads stall, right? Later, bank 0 becomes not busy. Memory controller takes thread B's request and schedules it over there. Then bank 1 becomes not busy. Memory controller takes thread B's request and schedules it. And while these two requests are going on, thread B stalls because it doesn't have its data yet. But now thread A can continue computation because its requests are serviced in parallel and they're done, right? Now, when thread B's requests are done, the thread B continues computation. What we've done is by servicing the requests of thread A in parallel and then thread B in parallel, instead of serializing each thread's requests, we've saved a lot of cycles on thread A. And the average stall time is approximately 1.5 bank access latencies in this case. So I've shown you these two principles, right? Basically, I've actually given you the first principle. How do you preserve parallelism? A parallelism aware batch scheduler operates on two principles. First, preserving parallelism of each thread. And you do this by scheduling requests from a thread to different banks back to back. This preserves each thread's bank level parallelism. The downside is, as I told you, this can cause starvation, right? Because once you schedule requests from a thread back to back, if the thread is continuing, it generates more requests, and you could be servicing only this thread in the system for a long time. So to prevent starvation, we're going to adopt the idea of request batching. And the idea is to group a fixed number of oldest requests from each thread into what is called a batch. and service that batch before all of the requests. And we're going to form a new batch when the current one is done. This, it turns out, it eliminates starvation because you ensure that the next batch is not serviced before the previous batch, and provides fairness. It allows for optimizations within the batch, as we will see. I've shown you this cartoon before. Basically, the memory controller forms a batch. Within the batch, it preserves each thread's parallelism, and it doesn't include the requests coming into the batch because that would disable that starvation guarantee, right? And the memory controller takes thread 1's requests, serves them in parallel, thread 2's requests, serves them in parallel, and thread 3's requests and serves them in parallel. So it's a regular memory scheduler that preserves each thread's parallelism, and then moves on to the next batch. So there are two components, and there are questions on how do you actually implement these two components, right? The first component is request batching, and the second component is within batch scheduling. That's parallelism aware. Let's take a look at each component. Request batching is actually easy to do. Basically, each memory request can have a bit. We'll call that the marked bit associated with it. And to form a batch, the memory controller marks up to marking cap oldest requests per bank for each thread. And this is the cap you were talking about. And this is an important cap to determine, actually. These marked requests constitute the batch. And once there are no marked requests in the memory request buffers, the memory controller forms a new batch. And that's how it works. And memory controller prioritizes marked requests over unmarked ones. There are no reordering requests across the batches. As a result, there is no starvation. Then the key question is, how do you actually prioritize requests that are marked, that are within a batch? Actually, you can use any existing DRAM scheduling policy for this. You can just use batching and any existing DRAM scheduling policy with it. For example, you can use FRFCFS, row hit first scheduling, which exploits row buffer locality. But we also want to preserve intra-thread bank parallelism, so we want to service each thread's request back to back. Right? And the idea to do this, as I briefly told you earlier, is to compute a ranking of threads when the batch is formed. When you form the batch, you also rank the threads somehow. And higher ranked threads are prioritized over lower ranked ones while the memory controller is doing the scheduling. The benefit of ranking is this improves the likelihood that requests from the same thread are serviced in parallel in different banks. Because different threads are prioritized in the same order in different banks, right? Across all banks, actually. So if you would like to do this, then the key question is, how do you actually compute this ranking, right? There are many ways of doing this ranking. You could, for example, say, come up with a random order across threads. And we've actually explored that in the paper. That doesn't work as well. It's not too bad, but it's not that good because of the reason that I'll show you in the next slide. So ranking scheme actually affects both system throughput and fairness. Again, we have two goals. We want to maximize system throughput. We want to minimize unfairness. And unfairness is still, we want to equalize the slowdown of different threads. To maximize system throughput, remember the red parts where the thread is stalling? We would like to minimize those, right? Minimize the average stall time of threads within a batch. To minimize unfairness, we'd like to service threads with inherently low stall time early in the batch. So if a thread has very low stall time, it's not very memory intensive, we'd like to service those earlier. Why? Because if you have two threads, one is not memory intensive and one is memory intensive, if you delay them by the same amount, the effect on the thread that is not memory intensive is a lot higher. So if you, let's see if this one works. Oh, the green one didn't work right. So I should use the blue one. So let's say this is a non-intensive thread. Its stall time is this much to begin with. And this is an intensive thread. Its stall time is this much. If you delay this thread by this much and the other thread by this much, you see that this slows down a lot more because it's needing only this much from memory. Right? So that's the key insight. Delaying memory non-intensive threads results in high slowdown. So we'd like to not do that. And we'll use this insight later on again. So this leads to shortest stall time or shortest job first ranking. And this is very familiar for those of you who've done scheduling. And if you have a single server queue with no row buffers and nothing, this provides optimal system throughput, and this has been known for a long time, obviously. But this is not, we're not going to claim optimal system throughput here because we don't have a single server queue, right? We have lots of banks, lots of complicated interactions between different like parallelism that doesn't exist in these assumptions, and also the row buffer. So the idea is to estimate the stall time of each thread within the batch and rank the threads with shorter stall times higher, because these are threads that have shorter stall times.
Can I change that?
Okay, go ahead.